You're probably getting a sense that there are a lot of time-honored problems that are assigned in first-year physics to help illustrate some major concepts and ideas, one of which is the Atwood's machine. So here's a little information that I copied over from Wikipedia if you're interested in the history behind the Atwood's machine. So it was invented by George Atwood in 1784, and it was mainly a device to help verify Newton's laws in a way. So let me draw a different diagram aside from Atwood's original design. A more simplified version of Atwood's machine, or depiction of it, goes something like this. You take a single pulley, mount it from the ceiling. Now, this is something we might refer to as an ideal pulley, in which the bearing is entirely frictionless and the pulley itself is very lightweight. It doesn't contribute much mass. So we take a single piece of string, wrap it around the pulley, and we're going to connect two separate blocks. So what we have is a system made up of two distinct objects. Oops. There we go. I guess this is somehow related to a dumbwaiter, if you're familiar with that. Okay, so let's call the blue one M number 1 and the red one M number 2. And for the sake of this problem, let's assume that M1 is larger than M2. If that's the case and the system is released from rest, then it's going to have an acceleration such that M2 accelerates upward and M1 accelerates downward. So the question might go something like this. Derive a formula based on based on Newton's second law to make a prediction of what the acceleration of the system will be. And there's a few ways to go about this, and I'll show you both methods. So method number 1, treat each block individually. And we'll try a second method where we'll apply Newton's laws to the whole system. Both of them are an attempt to find the value of the acceleration. So let's start with method number 1. Free body diagrams are the key to all derivations involving Newton's laws. So we can make a dot over here to the right of mass number 1 and try to identify all the forces acting on it. And we'll also make a dot over here to the left of mass number 2 and show all the forces acting on it. So let's see, we know that block number 1 is going to accelerate downward if its mass is greater than block 2. The driving force behind that is obviously the weight of that block. So there's a force vector pulling down equal to, you might want to say mg, but let's be careful, we can be more specific and call that m1 times g. Now there's also the tension in the string, right? That cord that passes over the pulley applies a tension to each of the blocks. For block number 1, that tension pulls upward, and I know to draw that upward force vector smaller in magnitude than the downward pull of gravity because we know the acceleration is going to be downward for block 1. So we'll call this T. Okay, now here's the thing. That tension is continuous all the way throughout the string. So over here, where it's attached to block 2, the upward pull on block number 2 is a force vector whose length is every bit the same as it was drawn for block number 1. It's the same tension applied to both of them. The difference is that tension must be greater than the weight of block number 2. So I draw the length for the vector that represents m2 times g as being shorter than that tension. And what's the reason why? Because I know the acceleration for that block is going to point upward. Okay, so given those two free body diagrams, how do we use Newton's second law? Newton's second law says the sum of all forces is mass times acceleration. And by looking at our free body diagram, we can come up with the sum of all forces for block number 1. It would just be equal to m1 times g minus t. We take the larger force in the direction of acceleration and subtract from it the smaller magnitude force opposite the direction of acceleration. So m1g minus t has to be equal to m1a. For block number 2, we'll use the same approach. So we have a kind of interesting frame of reference. It's not so much that up is positive and down is negative. Instead, we just say the direction of acceleration is positive motion. So for determining the net force on block number 2, again, it's the larger force in the direction of the acceleration minus the smaller force opposite the direction of acceleration. So we get T minus m2g. That's a way of saying net force. And by Newton's second law, net force has to equal ma. And there we have it. Now, something interesting happens if we take these two mathematical equations and add them together. So as a system of equations, when we add it up, positive t and negative t cancel one another out, and we get m1g minus m2g is equal to m1a plus m2a. So let's do a little simplifying. We can factor out the g on the left side. So g times the quantity m1 minus m2 is equal to a times the quantity m1 plus m2. And let's rearrange a little more so we can solve for a. It looks like a is equal to g times this ratio that's determined exclusively based on the masses. It would be the quantity m1 minus m2 in the numerator divided by quantity m1 plus m2 in the denominator. And if you want some numerical examples, we could say, what if the block that accelerates downward is 4 kilograms and the one accelerating upward is 3 kilograms? What would be the acceleration of our system? So in that case, for example, the acceleration would be 9.8 meters per second squared times 4 kilogram minus 3 kilogram over 4 kilogram plus 3 kilogram, or in other words, the acceleration would be 9.8 meters per second squared times 1/7. 1/7 of 9.8, if I'm not mistaken, is 1.4. So the acceleration of the system is 1.4 meters per second squared in that example, meaning the red block accelerates upward at 1.4 meters per second squared, while the blue block accelerates downward at 1.4 meters per second squared. The system has a common acceleration, provided that the string attaching the two of them is inextendable or rigid, however you want to say it. What about this second approach by just viewing it as an entire system? Okay, let's draw the Atwood machine again. M1 is the larger mass, M2 is the smaller mass. The system accelerates in the direction shown in this diagram. And now we just want to consider the external forces to the whole system. So one force external to the whole system is the weight of the larger block. So m1g pulls in the direction of acceleration, while at the same time, the smaller weight, m2g, is pulling opposite the direction of the acceleration. Now in this case, because we haven't isolated the two objects as being separate, the tension in the string connecting the two now becomes an internal force. And as you know from the previous lesson, when we state Newton's second law as acceleration equals net force divided by mass, we're only interested in external forces. So when viewing it as a whole system, the external force is basically m1g minus m2g. And then I need to divide that by the mass, but in this case it's the mass of the whole system, which would be m1 and m2 added together. So again, all we need to do to simplify is factor out the g, and we get the exact same expression we had from our first method. The acceleration is g times this factor based exclusively on mass that can be found by subtracting and taking the difference between mass in the numerator and dividing it by the sum of the masses in the denominator. So it's kind of nice to see that two different approaches yield the exact same result. That's the Atwood machine. Thanks for watching.